So I work in Spain, close to Barcelona, in Tarragona, and my background is polymer physics. So we also use poisson-boltzmann equation, and I will show how we apply it to interpolyelectrolyte complexes. So interpolyelectrolyte complexes is just the field where which we want to apply in the drug delivery vectors. So drug delivery vectors, so they should be spherical, self-assembled, nanoscale, biocompatible, stimuli responsible, and nanoparticles. So usually they are visualized like this. And there are two options for drug delivery vectors. There are traditional micelles, which are self-assembled from block copolymers. So you have a hydrophilic, hydrophobic part. And due to van der Waals forces, they form a hydrophobic core and with a hydrophilic corona. And because it is just created by van der Waals forces, it is unstable. So it has a CMC. It should have a concentration higher than a critical micellar concentration to form this micelle. But still in this state, they can assemble and disassemble. And another option is to use polysorbs. Then they are grafted to a chain, and then you can form such objects, and they are partially stable. But if you use polyions, so that's a chain positively charged and another chain is negatively charged, in this case, you can form aggregates which are much more stable because they are charged, and this the positive charges can interact with negative charge, and this object will be much more stable. So interpolyelectrolyte complexes, what is the ingredients of these systems? So they are polyanions with their contra-ions and ions, and polycations also with their ions. You can have spherical shaped aggregates which can contain several molecules of polycations and several molecules of polyanions. And you have also free chains in the solution which can be charged of both sides, and free ions and contra-ions which just surround the complexes. And so you may also have this neutral chains which will stabilize the size of these aggregates by steric repulsion. So this is just the system what we study. And how we study, so we have a mean field model of interaction. So it's of one chain which is positive charge, another is negative charge. And if they form an aggregate with M plus chains of positive charge and M minus negative charge, so and M plus and minus is not fixed, but it can be any size. So in this case, we just need to sum over all types of aggregates, where 0, 1 and 1, 0 will be unimers of each side, of each sign. And so we have entropy of these objects and free energy of each object. So if you sum over all possible compositions, so we have a free energy, and the energy of the object will contain electrostatic term and corona term. And it's if you minimize this free energy with respect to this concentration, but in fact you can get the probability distribution function of this size, over the sizes. And this it's already equilibrium, so you will have it will depend on the energy of individual chains in the solution and the energy of the aggregate. So we studied two possible situations. Then this object is stabilized, the size of the object is stabilized by neutral corona of this neutral chains. And another one, then you have a asymmetric system with a large asymmetry in the linear charge. Then you can have also loops which will protect this object, because if you don't have this, they will aggregate and precipitate, and it will be just neutral system. So if you want finite size objects, you need to stabilize them with neutral things. So I will just focus on this particular situation. And so we write a poisson-boltzmann equation for spherical complex which contain m plus and minus chains. In this case, it's just it's a standard procedure that you already know, that you can have salt concentration, and then if you renormalize the Poisson-Boltzmann equation, you can have also for weak charges Debye-Hückel approximation, and also you can have for salt-free regime, so you can solve analytical equation for salt-free regime. And so the results are the following. So you have a potential as a function of radius, and if you normalize with respect to the radius of this object, so you can have this to show this is just look like this, and here you have it's a step kind of step function, and the ions can penetrate inside the core, and they can partially this is the ions, and then they can penetrate inside the core for different charges, and then they can partially neutralize the core. And then we can also get the charge distribution in this size the core, and also we have three different charges. So this is the charge which is effective charge. In fact, this is a charge which take into account the contraions and the salt molecules which are inside the object, and you see that for 8K scales in this form, and and another one is the charge which appears at a long distance. In fact, if you are far from this object, you see this charge. And so this charge, Z3, this is a long distance charge, is in fact, you can see that it should be proportional to the charge of the bare polymer in a Debye-Hückel regime of this high salt concentration, but it will deviate for Poisson-Boltzmann regime. So, and we write the electrostatic energy in this form, so this also divided by the infinities to not to have infinite terms in the energy, and also we suppress the reservoirs just to have zero at infinity when they have a lot of things, and then the energy will also be on this form. And another ingredient is the individual chain, and the electrostatic contribution of this chain is we do it in like a charged rod, and then we have also similar electrostatic energy. So the energy this is Mannering parameter, which is related to linear charge density and different salt concentration, so which will have this. And so if we put all together and then we calculate the distribution function of this object, so we can have this structure. For example, here we have M plus is the number of positively charged chains in this in the aggregate, and M minus is the negative charged chains, and you see that they are all lie on the electron neutrality, close to electron neutrality line, so they are slightly charged, and they cannot be too charged because this contribution from the charges is too high. And if you change the salt concentration, this peak can move along this line. And this is the peak, and it is discrete because the number of m plus and minus is discrete. So that's why you have some peaks, and it is not line this portion. And so if you have depending on if you change the concentration, you can also have this position of the peaks, and for different parameters, for example, if they are symmetric, you will have it in a symmetric phase. And in fact, it is possible, yes, to see if they are not symmetric, you have it also in some places. And in fact, if you see this picture, it is possible to put it in a program. So we just developed EPEC solver, where you can have the parameters of one chain and then the parameters of another chain, and then you can just change the charge, the length of the blocks, and length of neutral blocks for each of them. And you can have all these solution properties, and it will calculate almost immediately the optimal size of the object, also the radius of this object, and the distribution of this object around the core. Yes, you can have it, you can solve it in Debye-Hückel approximation or poisson-boltzmann approximation. And so this will solve for each point of this grid. Here you have m plus and minus, and this is distribution function of this aggregates. And it will solve Poisson-Boltzmann equation for each grid and then calculate the optimal size of this object. And this is for different system. It will be like this. So our future plan is to include the effect of pH and elasticity of the core, because it can also be swollen and collapse. For some polymers, this effect can be quite significant. And also I will mention about our mean field approach, which we will also use together with this program, and it is a work in progress. So in fact, this method, which is called single chain mean field theory, is originally is dated from very 80s, and it was originally proposed by Ben Schau, Schleifer, and Gelbart. And then the ideas are very simple. So it's very simple. It's very close to DFT calculation for electrons and atoms. But here you have a polymer chain of any of any structure. So you may have a linear chain or branched chain or any structure. And so instead of calculating interactions of this molecule with the surrounding molecules, you consider that surrounding molecules form a field, and you calculate the interaction of each bit of this molecule with this field. And then if you have, and the fields are calculated on the basis of probabilities of each conformations. So this is mean field theory in that it doesn't have correlations and fluctuations, and it is a self-consistent field theory. So because these average fields are calculated on the basis of conformations of the chain, but the probability of each conformation is give you also self-consistent closure. So instead of many chains in the solution, you have only conformations of a single chain in the field. And this simplifies a lot the calculations. And in addition, it gives you possibility of parallelization. So because nowadays the clock speed doesn't improves, and this method is perfect for shared memory platform, because you can generate chains. In fact, you can. This is like in Monte Carlo simulations. You generate conformations of a single chain independently of each other, and so you can do it on the individual core of the processor, and you just test the probability of each conformation in the field, and then after that you calculate the field, and you can again see if this array of conformation you can store directly in the memory. So we have a cluster, and which has in particular 32 processors machines, and this method is very perfectly scalable. So this because you don't have correlations basically in between the molecule, and we apply it to model phospholipid molecule with 3 levels of coarse grain. So we have the most coarse grain, it was 3-bit model and 10-bit model, and this is 44-bit model. And so we just generate these conformations, and we sample the conformational space with with the Monte Carlo sampling, and we store this in the memory. And when we calculate the fields, and we can have a self-assembled structures like this, and these parameters of this model can reproduce the real experimental data for phospholipid bilayers. And what we have, yes, instead of calculating interactions between the molecule, we just calculate in interaction with the field. And so this method, so this consists of 3 independent blocks. So we have a module which generate conformations, and you need to sample the conformations of this chain. And another one, this has defined the interaction potentials between each bit of the model with the field. And another one is you define the geometry, how to split the space into grid. And here you may have a 1D spherical geometry. So if in case you have a symmetry, for example, radial symmetry or cylindrical symmetry, so it simplifies a lot and speed up calculations, because you don't need to divide in shells. You can use this symmetry. And so special geometry can be just anything you want, and it's again, it has you just write a free energy, and this free energy has terms, entropy terms and interaction terms, and these brackets is just the average over conformations of the chains. And if you write the probability distribution function of all these molecules with this approximation, so instead you have a probability which are decoupled, and this is a key for parallelization, and you have an entropy term and energy term which look like this. So, and you can minimize this free energy and get the probability of each conformation in this form. And if you want to include the electrostatics, it will be just additional term in this effective Hamiltonian, because you can write a poisson-boltzmann equation in integral form, and this is just perfectly compatible with the approach, because the Poisson-Boltzmann is also mean field approach, and has no correlation and no fluctuation, just exactly the same level of approximation. And this is the performance of this model. So you have we have a concentration of so the position or this concentration of each groups of the lipid molecule. We have CO, COH, and then we can see the distance from the center of the bilayer. So we can compare this information directly with molecular dynamics and real experimental data from neutron scattering. And in fact, this was done for 3D models that I showed, that you can have a good agreement, just numerical agreement with this data into all these mechanical properties, and which you have an equilibrium. For example, the thickness of the bilayer and interfacial area per lipid and compressibility constant. And what we did, just we continue to do this work with it. We improved this 10-bit models, and we have almost this lipids which has very similar structure. For example, only the length of the tail. So we just have one set of parameters to represent all these lipids, and so we see the performance can be quite good. For example, for all this area volume per lipid, area per lipid, membrane thickness, compressibility thickness. So you just match all this space, and this how this looks. So we have a hydrophobic. We can also consider interaction of these membranes and with different nanoparticles and polymers. And so this more or less all what I want to say. So this is people who work. There are different subject what we study. And so we have also some resource which describe what we are doing. So that's